This is Bob Romanoff,
CEO
of Romanoff International Supply Corporation. I'm going to speak today about porosity and how it interacts with the quality of your castings, what causes porosity, and how to eliminate it and how to produce better parts by following my suggestions. The causes of porosity today are still shrinkage and gas, just as they were when I wrote my first article on porosity in 1976. However, most of the porosity that we see in jewelry castings today is shrinkage porosity, which results from the metal contracting during freezing and solidification. There is a difference in appearance between shrinkage porosity and gas porosity. Gas porosity generally shows up on the surface of castings, let's say in rings, as irregularly shaped bubbles, as opposed to the pinpoint or worm-like porosity, which results from shrinkage. The worm-like shrinkage porosity generally shows on the surface only as a small pinpoint, or in a raw casting as a dark spot on the inside or outside wall of a ring. When that ring is polished, that small pinhole then sinks into the surface of the casting and either shows up as a single worm, or the entire surface shows up as a generally spongy area. Under magnification, shrinkage porosity shows up as a fern-like crystalline structure known as dendritic growth. It is not uncommon for people to confuse shrinkage porosity with gas porosity. Some shrinkage porosity might also be confused with what is known as a hot tear, which is completely different and will be explained later. Gas porosity can also occur in the same piece along with shrinkage porosity and hot tears, although all three usually occur only in the heavy sections of the casting. The most common causes of shrinkage porosity can be found in the design of the jewelry pieces itself, primarily in very abrupt changes from heavy sections to thin sections, or vice versa. It can also occur when the sprues that are used are too small and insufficient to keep the hot molten metal feeding the area of the ring, which is cooling and shrinking. Another cause of shrinkage porosity is the placing of castings too close together in the flask. This makes it more difficult for the heat to escape through the investment and doesn't allow for the rapid chilling of the castings. Relatively slow cooling of the castings promotes porosity. Shrinkage is a feeding problem. One way to recognize if the shrinkage porosity is caused by either incorrect flask temperature or metal casting temperature, as opposed to improper spruing or feeding, is to evaluate the quality of the casting. If the same rings show up with porosity in the same area on a consistent basis, that is generally an indication that the ring is fed insufficiently and or improperly. If the location of the shrinkage porosity is different from tree to tree of the same style ring, then the cause is probably the inconsistency in the temperature of the metal or the flask, which is causing the problem. The ideal sprue or feed attached to a ring should be designed to promote progressive solidification. Those are two very important words. This means that the heaviest part of the casting is fed directly by a heavier sprue, about 50% bigger in size, and the sprue in turn is fed by a still heavier sprue, which is the tree trunk of the waxed tree. That in turn eventually leads to the button at the bottom, thereby encouraging the shrinkage to take place progressively toward the bottom of the cast. In a correctly designed combination of sprue and ring, the first place to solidify should be the casting itself. If this progressive solidification does not take place, then the shrinkage will probably take place in the ring, where you don't want it to be. Casting temperature as well as flask temperature are also extremely important. Flask temperature, in order to minimize the variables in casting, I usually recommend that a caster keeps his flask temperatures constant for everything he will cast in a particular oven. The reason being that although he may change the temperature of his controller, the only thing that really changes in temperature in 10 to 15 minutes are the temperature of the oven. The interior of the flasks actually take a minimum of 30 to 60 minutes, depending on their size, to change to the new desired temperature. Therefore, there is no practical way for the caster to know exactly what flask temperature he is casting if changes are made. I generally recommend a flask temperature of 800 degrees Fahrenheit for thicker designs, up to 1,000 degrees Fahrenheit for average designs, depending on the thickness of the castings. These numbers generally apply to gold alloys and silver. platinum flask temperatures are from 1600 Fahrenheit to 1650 Fahrenheit. Sometimes a flask temperature of 1000 F to 1200 F is required for thin sterling castings due to the nature of metal. The following illustrations you're about to see indicate some common casting issues. Diagram 1 shows the incorrect way for a sprue to enter a ring. It shows 90-degree corners as indicated by the arrows. When the metal enters this ring, a certain amount of turbulence will be created. This will result in a pickup of air which is being introduced into the ring cavity. The proper method of having a sprue enter a ring or any other jewelry design is to have a flared entrance, as in diagram 2. There, the sprue is flared so that a smooth and uniform flow of metal will be able to enter the casting without turbulence. The spruing technique illustrated in diagram 3 shows sprues being used to enter the 3 heaviest portions of that particular casting. This would allow the heaviest portions to be fed sufficiently to minimize the shrinkage porosity described earlier. If the metal entered only one of those particularly heavy areas, it would then have to travel through several thin areas before getting to the other heavy areas. The result would be that the most shrinkage would take place in the heavy areas, since the thin areas leading to those heavy areas would freeze and solidify first, therefore cutting off the source or feed of molten metal required to minimize the shrinkage, which you don't want. The ring in diagram 4 is an example of the second temperature range referred to earlier, whereby the 2 metal streams have not met to form a homogeneous casting. And at that particular point, because the metal was not hot enough for the 2 streams to solidify together, this symptom would also indicate a hot tear. The ring shown in diagram 5 shows some balls on the inside and outside of the ring, the result of insufficient or improper vacuuming of the investment. Either the operator's vacuum pump was not strong enough or insufficient time was allowed for the air to escape the investment. The answer is to get a vacuum investing machine, which is available in all sizes. This will eliminate any chance of bubbles on the casting, and I'm going to show those particular machines now. This is an example of an investment mixing machine, and they come in different sizes. There's a smaller one, there's a larger one, and there's also a larger one on the other side that I'll show in a moment. The investment goes in here, water goes into this tube, it's filled up, and when you turn the machine on, it automatically takes the correct amount of water out of here, goes into the upper chamber, you turn the machine on, and this stainless steel blade turns and mixes the powder, investment powder, with the water to a uniform slurry. After about 3 or 4 minutes, which it also mixes under vibration, the flask is sitting underneath here in this lower chamber, and when it is ready, you stop the spinning of the blade, pull this handle out, and the investment goes into the flask and fills up the flask. Whether it's a perforated flask or a solid wall flask, it doesn't matter, whatever you put in here. And then you turn the table, which is turned automatically with the controls down here, to the next flask. Close this again. When the next flask is underneath the chamber that is filled with this investment slurry, open it up, flask fills up, close it, and continue doing that until all the flasks underneath here are filled with investment. And the benefit is that all this is taking place while it is under vacuum, so there is no chance of bubbles on the castings. You removed all the air from the investment while it's in the upper mixing chamber, and when the investment goes into each individual flask, the air is being removed from it. So once again, there are no bubbles on your castings, which helps the quality of the casting. And also by vacuuming the investment during the mixing procedure, you're also making it much smoother and more homogeneous, so the surface of the castings will be better when it's done in this process. This is a larger vacuum investing machine, and they come even larger than this. This one would be used for very big diameter, tall flasks, up to 12 inches tall, for someone who's casting a lot of rings or other pieces on an individual flask. Once again, this is the chamber where the powder and the water goes in. It mixes under vacuum, and then once again, as you turn the table from one flask to the next, you open up this valve, the investment and the water goes into the flask, fills it up, you close the valve, turn the table again, fill up the next flask until all the flasks are completely filled. And most important of all, it is mixing under vacuum in the mixing chamber, And when the investment goes into the flasks themselves, it's also under vacuum, to once again, the purpose being to eliminate any bubbles on the castings. The ring in diagram 6 shows a white inclusion in the casting, most probably investment particles. This is the result of investment breaking off at the entrance of the tree when the metal entered. The ring in diagram 7 shows a black spot in the casting, most probably a graphite inclusion from the crucible. Here, graphite flaked off from inside of the crucible because the crucible was used beyond its normal life or was a poor quality graphite. The ring in diagram 8 is probably an example of a casting which was made from a wax pattern that had shrunk considerably. The wax operator did not notice the shrinkage in the wax surface before setting the ring up on the wax tree. Waxes should always be inspected very carefully before being put on the tree. This is quite common in a design where there is a large, broad, flat surface which encourages shrinkage on the surface of the wax. The easiest way to eliminate this problem with a simple wax injector, which I will show you in a moment, is for the operator to hold the mold against the wax injector nozzle for a sufficiently long period of time, minimum of 30 to 40 seconds, so that the wax solidifies before the mold is removed from the nozzle. This would allow the wax to solidify while the wax is under pressure, thereby eliminating the sink in the surface of the wax. You might also use a wax with a faster setting time. The best answer is to get an automatic vacuum wax injector which can be programmed to control this. This is a standard wax injector which has been around a long time. In fact, my father made the first wax injector about 50 years ago, and they've been used all that time. It's not expensive, and basically it is a heated tank with thermostat control so that the wax, generally at about 160 degrees Fahrenheit, is melted in this chamber. An air compressor with an air line is connected to the top here, and with 160 degree temperature wax and between 5 and 10 pounds air pressure, when you push the mold, this is a rubber mold, when you push the rubber mold with an aluminum plate on the top and the bottom of the mold against the nozzle of the wax injector, like so, and push it in, the valve opens inside the wax injector, and under heat and pressure, wax flows in and fills up the wax cavity. Then you wait a moment or two for the wax to completely solidify, open up the mold, and remove the wax from it. Okay? Very simple. The disadvantage of this is that the operator who's holding the mold against the wax injector sometimes might be squeezing the mold very tight, and by squeezing it very tight, he could be squeezing the cavity in here, and you end up with a distorted wax, which is not as round as you would like it to be. If he or she doesn't hold the mold very tight and it's loose or not clamped that tightly, then the wax will come out larger than what the original intention was. And if you have a heavier wax, that heavier wax is going to translate into a heavier gold, silver, or platinum casting. Which means that when you are pricing out your jewelry and you price it out for a wax that should only weigh 2 or 3 grams, if it weighs more than that, your gold casting is going to come out larger, and you're going to be giving the customer more gold than you originally anticipated or that you allowed for in the price of the piece that you're selling. Then vacuum wax injectors came out. And the advantage of the vacuum wax injector, as I pointed out in the simple machine, wax flows in. But in order for wax to flow into the mold, the air has to get out. And one method of doing that is that mold makers would cut air releases in the mold, which was not the best solution, but it was the only solution to allow the air to maybe escape. But all of it doesn't come out, and it acts as a resistance to the wax going in, which means you're not always going to get a perfect pattern that did not fill into all the detail. As you can see on this particular ring, there's a lot of detail, and if you want all that detail to fill, you have to make sure that the wax can flow easily and fill it up before the wax solidifies. On a vacuum wax injector, the mold is simply put on a tray like this, okay? And when the machine is on, it also has 2 chambers, a heated chamber where the wax is also melted at about 160 degrees and also under pressure, but you control all of the factors. You could say, for example, this mold needs 160 degrees Fahrenheit, and it needs 8.5 pounds of pressure. And you also control the amount of pressure put on the mold. So when this clamp comes down, squeezes the mold uniformly and presses it against the nozzle of the machine, when it meets the nozzle of the machine pulls a vacuum on that wax cavity so that there's no resistance to the wax flowing in. So first, the mold is vacuumed, then instantly wax injects in with no resistance, and the mold also, under controlled pressure, which you set for the particular design that you have, the wax is going to come out the exact thickness and weight that you want it to, so that the gold ring, platinum or silver ring or part is going to come out at the exact weight in metal that you want it to be. So it's priced out correctly for the amount that you're selling that part for. So vacuum wax injectors pay for themselves in controlling uniform pressure on the mold, very, very precise temperature control, and also taking the air out of the mold before the wax goes in. The average wax operator in 8 hours with a standard wax injector can produce 400 to 600 pieces in a day, but it could have a reject rate of as much as 30 or 40%, that the wax is not absolutely perfect. On a vacuum wax injector, the rate is much faster because instead of you taking the time to hold the mold against the wax injector, the mold clamp is holding it against the wax injector, and generally that increases the production by at least 40 or 50%, and every wax is going to come out perfect because you programmed it for the pattern that you want to produce, and the program, the details, writing it right on the mold itself, so you'll know that when you take this mold off the shelf and you need so many pieces to fill your order, it's telling you exactly what program you want. The machine is programmed, and the waxes come out perfect and consistent every single time. About 15 years ago, we started selling 3D printers. 3D printers were a much quicker way of producing waxes than wax injectors, and also without the labor. A designer would put a design into the computer, create a file, and send the file to a 3D printer. The 3D printer would then produce it either in wax or in resin. Okay? Now, this is an example of resin parts, rings, and so on. Okay? Here is a little more complicated pieces. And here are some very artistic pieces that were created in resin, in the resin 3D printer, and some large bracelets that were created with extremely fine detail, as you can see, if you can see that detail. And this is a plate, the grow plate from a 3D wax printer. The resin printers are the Tiger 3D printer, which is a machine that's under $10,000. This has grown a much larger plate in wax, and this is a machine in the $55,000 range that produces a larger quantity of parts. This particular entire tray was done in about 10 hours. If it was just ladies' rings, for example, it might be done in 4 or 5 hours. These resin parts were created in 2 or 3 hours, depending upon the part and how high the part is. The advantage of a resin printer is that the machines are less than $10,000, but you do have to create supports when you're doing the file, which takes time. And then these supports, after the wax burns out and you cast them, these supports then need to be cut off, which also takes labor. The 3D printer, the ProJet machine, which we sell, can produce a plate this size with this many pieces. These very heavy pieces took about 10 to 12 hours to grow. If they were ladies' rings, it might have done it in 4 or 5 hours. The advantage of the wax printer is, besides, number one, wax burns out much more cleanly during the burnout cycle of casting, much more cleanly. Resin does not burn out that easily, and if you don't use the correct investment and you don't do the proper burnout cycle, they can give you a rougher surface on the castings or even crack the investment. Whereas the wax drains out at a very low temperature and the castings are very clean because the cavities inside that the metal is going to come in contact with is also a very smooth surface. Also, the other benefit is the major benefit, you don't have to build the supports as you do with the resin. Over here, the waxes are grown with the white support material and the actual design on top of it. After these are grown, these go into alcohol. The alcohol dissolves the support material underneath, and you have the waxes which are ready to be put on the tree without having to remove supports. And wax, as I said, burns out very cleanly. So this is the way most waxes are produced today. There are many large manufacturers and also casters, commercial casters, that may have had many, many wax injection machines like the simple wax injector or the vacuum wax injector, and have reduced that quantity to less than half by producing the waxes by a 3D printer. Diagram 9 could be the result of an improper burnout cycle. The problem can be that this operator has allowed the temperature in the oven to climb too rapidly during the first hour, so that the wax, instead of melting out smoothly and easily from the tree, has boiled in the cavity and broken down the surface of the investment to which it was immediately adjacent. The result is the rough surface that you see. Also, it will happen if the waxes are not placed at a 45-degree angle on the tree for easy drain out of the wax. This wax tree shows the correct way and the incorrect way of putting the waxes on the tree. And I've only done 3 waxes. The tree can certainly take a lot more pieces than that. The correct way to put a ring or any piece on a wax tree is that it should be set on a 45-degree angle. The main purpose is to be sure that the wax can easily drain out by gravity. This is the bottom of the tree. And the wrong way is to put the piece at a 90-degree angle. Now, somebody would say, well, I can fit a lot more pieces on the tree if I put it at a 90-degree angle. The problem is that as the temperature in the oven climbs and the wax cannot easily drain out, the wax is going to boil before it has a chance to drain out. And if it boils against the surface of the investment will be very rough, and that rough surface then translates into a rough casting. Also, you have to be careful. If you put the ring like this because you think you're saving space, the problem here is that the lower half of the ring over here cannot drain out from the tree, and also the surface over here will go very high in temperature, boil, and also cause a rough surface in the casting. So the only correct way to put pieces on a tree is that they be on a 45-degree angle so the wax can drain out very easily to the tree trunk, and from the tree trunk to the base, and so on. The ring in diagram 10 has a double sprue entering a very heavy section at the top of a signet ring. Many people use this type of sprue because if there is a design on the top of the ring in this heavy area, it'll be ruined if a sprue is fed directly into it. That should be pretty obvious. As a guide for casting temperature, there are 4 basic temperature ranges in which metal may flow into a flask. Each range will produce different results. In order to find the temperature at which perfect castings can be produced, you must first know the melting point of the alloy that you are casting. And every alloy and components that go into that alloy will determine what the temperature needs to be. So whoever you purchase your alloy from should give you an idea as to what that temperature should be. The first temperature range is from the melting point of the alloy up to about 75 degrees above the melting point, Fahrenheit. This range will sometimes produce incomplete castings because the metal is just not hot enough to form a complete casting. Usually everyone can diagnose this problem very simply. It means the temperature is too low. B, the second range is the one most people misidentify. It is usually about 75 to 100 degrees above the melting point of the alloy. The metal flows into the investment and forms a complete casting, but it is not hot enough to remain fluid when both streams of metal meet in the case of a ring. When metal flows into the shank of a ring from the bottom, it divides and flows around both sides of the shank. One side flows around 75% of the ring, while the other side of the shank only receives about 25% of the flow. The result is that the 2 independent streams of metal meet on one side of the shank. The result of these 2 streams meeting together in a semi-fluid state produces what looks like cold porosity. In effect, these 2 streams have met and solidified before they became a solid homogeneous casting. Most people will try casting at a lower temperature, which will worsen the condition and result in incomplete castings. The third temperature range is a very narrow range of 100 to 250 degrees above the second range. It is during this range that the metal will flow into the investment cavity at a temperature just hot enough for both streams of molten metal to meet in a completely fluid state. If the technique of progressive solidification, as previously described, is followed in this desired temperature range, the result should be a good casting. The fourth range is all temperatures above the third range. This will result in a ring or jewelry, which certainly fills in completely as in the third range, but being hotter in temperature than necessary produces excessive shrinkage as it cools down to its solidification temperature. As the casting temperature increases in the fourth range, the shrinkage in the heavier parts of the casting will be greater. It is extremely important to remember that the temperatures mentioned in these four ranges are to be used as a guide only. Other factors, such as the sprue diameter, the length, the flask temperature, type, and thickness of castings, etc., will determine the exact temperature for producing perfect castings, which will require definitely experimentation on your part until you arrive at the right temperatures. Hot tears. Hot tears are related to very high internal stresses on the casting. They occur when a section of the casting is unable to expand or contract as the metal is cooling and shrinking in its normal manner. Most of the time, hot tears are caused by an abrupt change. For example, going from a heavy section of the casting to a thin section of the casting while making a sharp bend or a sharp angle. The methods for eliminating or minimizing hot tears are to design the model so that there are no heavy and thin sections occurring at a point where there is a sharp bend or 90 degrees in the casting. To add a sprue to the heavy section, which would allow the metal to feed more easily through that section of the casting, thus minimizing the stress placed on the casting at that particular point. Or to change alloys. Some alloys have more shrinkage than others and thereby creating additional stresses. Gas porosity in castings results from gases being absorbed into the metal during the hot molten state and remaining when the casting becomes chilled and solidifies. To prevent gas porosity, one must first prevent gases from being introduced into the molten metal by melting in a controlled atmosphere, which means vacuum and then argon gas. In the event some gases are introduced into molten metal, their escape before the casting solidifies should be made as easily as possible. Let's look at the introduction of the gases. Metal, while in its molten state, is constantly trying to absorb gases, such as oxygen and hydrogen. When something is hot and molten, it needs oxygen to continue to burn, as in every fire needs oxygen. If we use a protective atmosphere for the metal, this will eliminate the introduction of gases into the casting. An example of a protective atmosphere would be the introduction of argon gas after melting the metal in a vacuumed chamber. The argon, since it is heavier than air, tends to form a blanket over the molten metal, thereby preventing gases from being absorbed by the molten metal. Melting the metal in a graphite crucible also minimizes absorption of gases, since the graphite crucible produces what is known as a reducing atmosphere. Molten metal will hold many more times the volume of gas that is dissolved in the solidified casting. During solidification of the casting, this gas may escape if the conditions are right. If not, it will remain in the casting and show up as gas porosity. An automatic, programmable vacuum casting machine is best for casting gold, silver, and brass or bronze. This includes the Endotherm and Yasui casting machines. This is an Endotherm VC40V casting machine. It handles all of the issues that are related to gas and shrinkage porosity in your castings. Metal is put into the crucible, okay, into the graphite crucible. There is a thermocouple that sits into the molten metal, reading the temperature very, very precisely. The machine is programmed to follow all of the necessary procedures for producing good castings completely automatically. It is first programmed on here for the correct temperature, the vacuum, introduction of the argon gas. When it reaches the correct casting temperature, the thermocouple comes up, and like a plug in a bathtub, the metal drops into the flask, which is sitting in here. This machine will take a flask up to 5-inch diameter by 9 or 9.5 inches in length. It uses a perforated flask. The benefit of the perforated flask is obviously when you pull a vacuum on this, investment is porous, and it will pull through the flask, creating a negative atmosphere inside the cavities, which are the jewelry after the flask is burned out and so on. And that vacuumed atmosphere in the flask, combined with very precise temperature control, the metal melting completely under vacuum. This chamber closes, so there is a sealed vacuum chamber here that the metal melts in. And you've programmed it for the temperature that you know is going to give you the best possible castings. When it reaches that temperature, as I mentioned, the thermocouple comes up. The chamber goes from vacuum to overpressure so that the casting is filling under gravity as the metal drops down, the pressure from the chamber, and also the endotherm machine has a vibration feature, which is very important. If you have a glass of sand and the sand is sitting still, when you vibrate it, the sand settles down and becomes much more dense and compact. So that casting, once again, is filling by gravity, by overpressure, and by the vibration, as well as a vacuum pulling on the flask to help pull the metal into the cavity. And the result is, if you have arrived at the correct temperatures between metal temperature and flask temperature, you should get a very good casting. They also make a smaller version of it with the same qualities and benefits. This is the MC20V, which, once again, you put the metal into the crucible, you would put the flask into the machine. As you can see, this is the crucible ready to take in the metal. It shows the inside chamber of the machine. There's the crucible. The flask goes in, and all this is done at the same time. This is also programmed. You've set this for the correct temperature. That gives you the best castings. As I said, put the metal in, put the flask in, close the door of the machine, lock it, hit the start button, and when you hit the start button, the metal starts to melt under vacuum, okay? And it will climb up to the temperature at which you get your best castings. And if you're casting with a yellow gold alloy though, which will have zinc in the alloy, you will hit the pause button and let argon gas be introduced. You reduce the vacuum and argon gas flows in, and the purpose of that is by reducing the vacuum and introducing the argon gas, you prevent the zinc, which is in the alloy, from vaporizing out, because the zinc melts it in the 800-degree range. And if you don't do that, the zinc will vaporize out of the alloy, and you'll have less alloy, which will result in 14 karat going to either 15 karat or 16 karat, as I've mentioned previously, with other issues. When the reaches the correct temperature for casting, and it will indicate exactly when it has reached that correct temperature, you take this handle and tilt the machine over like this so that the metal pours at that correct temperature directly into the flask. The chamber is still vacuumed, okay? And you let it sit for a minute or a minute and a half. The metal goes from red to black, which means it has completely solidified. You bring this back like this and open the chamber. Take out your flask, pull it aside, and you can add your next charge of metal and then put the next flask into the machine and repeat the process. The MC20V is limited to a 3-inch by 3-inch diameter flask, 3-inch diameter by 3-inch high flask, which you can easily put 10 to 20 rings into. And the capacity of metal is, I think, 100 grams of gold and more than that of platinum. This machine will do gold, silver, and platinum, as well as stainless steel, okay? The temperature control for the metal is a thermocouple, which sits directly into the crucible and reads the temperature very accurately. And for platinum, it has an optical parameter which reads the surface of the platinum by infrared, okay? So it can do gold, silver, brass, stainless steel, and platinum in this particular machine if the capacity for yourself is sufficient with a 3x3 flask. This is the Yasui casting machine. It is similar to the Endotherm machine. The quality of both machines, Yasui is made in Japan, Endotherm is made in Germany. Both very, very good quality, and the principles are the same. It melts the metal under vacuum, introduces argon gas automatically. The flask is introduced. There is a vacuum on the flask pulling through the perforated flask, as I just described, and it is programmed to automatically go through all of those parameters based upon what is best for either 14 karat yellow, 18 karat white, whatever it happens to be, okay? You've programmed both machines, either the Yasui or the Endotherm, in advance for the particular pieces that you're casting. And then, frankly, what you should do is when you put flasks into your burnout oven the night before, they should be numbered 1 to 10 or 1 to 20, depending upon how many flasks you're going to be casting. So when you take number 1 out of the oven, and you hit program number 1, the casting machine will know exactly what parameters to follow in order to produce very good castings. The Yasui machine has all the features of the Endotherm. It's a little bit less expensive. It doesn't have the vibration feature, which Endotherm has a patent pending on. But they will both produce very, very good castings. All casting machines fall into 2 categories. Vacuum casting machines, which I just showed you, the Yasui and the Endotherm machines. Those are the best examples of vacuum type casting machines. They're very good for gold and silver and brass. When you want to cast platinum or stainless steel, it requires more force to get the metal into the cavity. And vacuum, even with the overpressure and everything, the other features that they have, are usually not enough to be able to fill very thin platinum castings, because platinum at 3,500 or 3,600 degrees Fahrenheit, when you are trying to cast it, it loses its heat very rapidly, and you need to get the metal in there as quickly as possible with the most amount of force. So centrifugal force is better. Consequently, centrifugal casting machines are better definitely for platinum and so on. And most people have a centrifugal casting machine for their platinum and stainless steel work, and vacuum casting machines for their gold, silver, or brass. Okay, now, the RCS machine, which is an exclusive model made for Romanoff, has certain features that are very significant. On other centrifugal casting machines, when the temperature of the metal is reached that you want to cast at, the coil drops away, and as soon as the coil that does the heating, the induction heating, as soon as the coil drops down, there's no more heat in the crucible, and the metal will solidify if it doesn't get out fast enough into the flask. On the RCS machine, which is a model made exclusively for Romanoff, the coil is a rotating coil that turns with the flask so that the metal is still being heated when the arm spins. And that's very significant because without the rotating coil and the coil drops down, you need to heat the metal hotter than you normally would to allow for the temperature dropping down to the desired temperature. Whereas on this one, you can actually cast at a lower temperature because the coil is still carrying the heat of the metal, and you fill the flask at a lower temperature. And whenever you can use a lower temperature, it generally will improve the quality of the casting. So, once again, you put the charge of metal into the crucible and the flask, close the door of the machine, and operate your buttons. There's a semi-automatic and completely automatic model of this RCS machine. The semi-automatic means it has complete control over the temperature, which is very important. And it also uses an optical parameter, which is shown here. And that reads the temperature of the metal when it's in its molten state. So that's how you control the temperature of the metal with this. The completely automatic one means that all you do is program it whether you're doing thin platinum pieces or slightly heavier platinum pieces or stainless steel. You close the door of the machine after you put the flask and the metal in, hit the start, and it will go through the completely automatic process. There is a difference in price between the semi-automatic, which means, as I said, with automatic temperature control, but you tell the functions right here in the button, which is not on the buttons, which is not a problem. Tell it when to melt, when to cast, when to introduce argon gas, and vacuum. And those are just done in the same way as the automatic one, except you're doing it manually. It's like the difference between standard shift transmission on the car and a completely automatic transmission on the car. They both get you from point A to point B. One automatic transmissions cost a little bit more than standard shift transmissions, okay? And this one size will take a 3x3 flask, 3-inch diameter flask, by 3 inches high, as I said, with the rotating coil. When you go above this particular size, to the CS1 machine, which will take a 4x5 flask approximately. It is the same thing. It doesn't have the rotating coil. The coil does drop down. So you do have to allow a little bit higher temperature to allow the temperature being reduced. But you do need that. You need this machine for the larger flask if you're doing larger pieces. And they also come as automatic, okay? Or semi-automatic. The reason it is best to use at least a 50-50 mixture of fresh to remelted carat gold alloy is that the zinc acts as a deoxidizer. So when it is lost in remelting, that property is lost as well. Now, a summary of pretty much everything that I've been discussing. Sprues should be round, smooth, and preferably straight in order to minimize the entrapment of gases on the way into the casting. Gas entrapment will occur if sprues are required to make 90-degree bends, which I explained the problems of before, which create unnecessary turbulence. It is important that the flash temperature be hot enough that the outside surface of the casting does not solidify before the inside surface. If the flash temperature is not hot enough, a wall will form around the casting, making it difficult, if not impossible, for any gases that have accumulated in the molten metal to escape before the piece completely solidifies. Ideally, you should want to melt metal as quickly as possible, bring it to the correct temperature, correct casting temperature, and then cast it into the flask the moment that it reaches that optimum temperature. Gas absorption in molten metal is really a factor of time and temperature. As the temperature of the molten metal increases and remains at a high point for a long period of time, more gases will be dissolved into the casting. Most casting machines used today can be programmed to melt the metal in a vacuum atmosphere and then introduce argon gas at the right moment. The right moment is just before the zinc in the alloy, as previously explained, will begin to vaporize out of the alloy and result in a higher karat gold. 14 karat gold could easily become 15 or 16 karat gold, which unfortunately is not going to be good for the pricing of your part. When the desired molten temperature of the metal is reached, the metal pours into the flask by gravity, under pressure and vibration to produce a clean, dense casting with minimal or no porosity. Gold, silver, and platinum are the same price all over the world. The significant difference is the labor cost in the United States and Europe against the very low labor cost in the Far East. A good, clean casting requires very little labor to finish it, and more important, when you have to do excessive polishing because of a poor surface, you are losing gold unnecessarily. Therefore, it is well worth having the right equipment and the right knowledge of casting to minimize your cost, or you will not be able to compete profitably. Romanoff International has the right equipment, knowledge, and experience to help you produce perfect castings. Thank you for your time.